Hello friends, I welcome you in the series of my lecture on generation of microwave signals. Previously we have seen like the microwave signal is generated by using a reflex klystron, but reflex klystron is an oscillator device and that generates the microwave signal which is having very low strength. So there it cannot be possible to run many applications with the help of that output signal. So we need to amplify that signal. That signal amplification can be done by using two cavity klystron instead of one cavity. So this two cavity klystron, while designing this two cavity klystron, the points need to be considered. That is, the transit time in the cavity gap is very small compared to the period of an input RF cycle. The next one, the input RF signal amplitude is very small compared to the DC beam voltage. Then third point which need to be considered, that is the cathode anode cavity grids and the collectors are all parallel. No space charge or debunching takes place at the bunch point. Then RF fields are totally confined to the cavity, no field in the drift space. The electron leaves the cathode with a zero initial velocity. So these points need to be considered while designing this two cavity klystron amplifier so that it can work as an amplifier. Now, considering all these points, the construction of this device can be like this. Like it will have a cathode, it will have an accelerating anode, two cavities as the name suggests, buncher cavity and catcher cavity, and the collector for collecting the electrons, as well as the input RF signal is required, which need to be amplified. Now, whatever is the device, either amplifier or oscillator, that carries the five processes while handling this microwave signal. The first is electron beam generation. Now there is a cathode and filament. Filament which heats the cathode so that cathode emits the electron. These emitted electrons will be form the electron beam. So the first process is completed. Now to form the electron beam having such a long length, we need magnets that will create an axial magnetic field so that electron beam will be continued from cathode to collector. Similarly, to travel this electron beam, accelerating anodes are there to accelerate the electrons. Now this electron beam will first enter into the first cavity that is called as buncher cavity. Now this buncher cavity is supplied with an RF input signal which need to be amplified. Now this RF input signal when in come contact with an electrons in the buncher cavity, that if a field will affect the electrons, that means the positive half cycle of the field will accelerate the electron or negative half cycle will deaccelerate the electrons. Now the width of this buncher cavity will be such a small that at a time only acceleration or deaccelerations will take place. So here the width is kept very small and the electrons which are coming in contact with this RF field, that will get accelerated and deaccelerated. In the first cycle they will get accelerated and in the second cycle they will get deaccelerated. So acceleration and deacceleration of the electron, that means the velocity modulations takes place. Like due to the acceleration velocity increases, due to the deceleration velocity decreases. So due to the increase and decrease of the velocity, as I explained in my previous video, the velocity due to as a result of this velocity modulation, when the electrons travel for some distance, there are chances like that they will meet at a one point. So that is initially the distribution of electrons are uniform, but now when they are meeting at a one point, that means the distribution is changing and that result into the density modulation. So first process is electron beam generation, second process is a velocity modulation, and third process, that is a density modulation, that has been takes place, and at the output of this cavity, at the output point of this cavity, the bunch of electrons are taking place. So this cavity is called as buncher cavity. Now these bunches of the electrons which are coming out from the cavity, they will travel towards the catcher cavity, where the catcher cavity is kept at a distance equal to capital L. Now this distance capital L is very large as compared to the distance d. As this capital L is very large as compared to the separation in between the cavity, or the width of cavity is the small d. So this L is very greater than this small d. So because of that, whatever the field inside the cavity, that will not affect the distance L or this length L. So field will get confined to the cavity, and this L, distance L or this length L in between the cavity is the space in between these two cavity L, that will be the field free space, or it is also called as drift space, drift space. Now this field free space, because of that, there is no change will takes place in the path of electrons, as there is no field. Similarly, what happens as this L is quite large, then when the electron reaches from Buncher cavity to Catcher cavity, by that time the phase of the RF signal has been changed. Initially, if the electron leaves the Buncher cavity, at that time the RF signal is having a positive half cycle. By the time it reaches to the Catcher cavity, RF signal has changed to its negative half cycle. So, whenever the electrons are moving from positive half cycle to negative half cycle of the RF field, at that time here in the catcher cavity, there is no acceleration of electrons, and as there is a negative half cycle, the electron will get decelerated, or the bunch of electrons will get decelerated, and they leave their energy to the field. Their velocity gets reduced, and they give out their kinetic energy. And that kinetic energy which is released by the electron, that will be catched by the RF field which is present inside this catcher cavity. Now, whenever the electrons are traveling from this catcher cavity, as there is a negative field, the maximum energy is extracted from the electrons, and these energy extracted electrons, the leftover electrons, are catched by the catcher cavity. If you see the catched by the collectors. If you see the total process here, initially the electrons which are moving from this puncture cavity, they will travel a distance L, and when they reach to the catcher cavity, if you see on the top waveform, when they reach to the catcher cavity, there is a negative half cycle. So because of this negative half cycle, maximum energy from the electron will be extracted by this signal negative half cycle, and the maximum energy is given to the cavity, that is inside the catcher cavity. In the catcher cavity, the element which is extracting the energy or catching the release energy from the electron is the RF signal. So, and the remaining electrons, they will be collected by a collector which is present at another end of the device. Now, whatever this RF signal catched by this cavity, or catched in the catcher cavity, that because of the energy catching from the electrons, the amplitude of this RF signal goes on increasing, or we can say that current of this signal goes on increasing. And this current is having many harmonics. If you compare this current if to the input current, then there are many harmonics of your input current, or the input signals are present in the catcher cavity. So you can have a minimum 15 harmonics of the input signal in the catcher cavity. Now this signal can be taken out by using any RF antenna or the loop antenna or RF probe we can insert in the catcher cavity, and we can extract that energy which is amplified signal, that is 15 harmonics of the original signal we are getting almost. So that will be signal is amplified by a large amount, and we are getting it in a output side that can be taken out, and that can be used for the various devices. Here, instead of, if we compare the replace klystron and two cavity klystron, instead of single cavity, two cavities are used. Now both the cavities are kept at a far distance from each other. Both the cavities are the reentrant cavities, and they are kept vertical, not an horizontal as that of a reflex klystron. And the signal which is emitted by, or the electrons which are emitted by a cathode, they will form the beam with help of axial magnetic field. They will get accelerated. They will reach to the buncher cavity. In the buncher cavity, there is an input RF signal is there. That input RF signal will accelerate or decelerate the electron, that result into the velocity modulation. So velocity modulation result into the formation of bunch of electron. Now this bunch of electron, when they reaches to the catcher cavity, when they travels through the length L, that is a dipped free space. So when they travels to the, or when they reaches to the catcher cavity, there is a negative RF half cycle is present that will extract the energy from the electrons, and this extracted energy from the electrons will become catched by the RF field which is present in the catcher cavity. And if you compare this RF field which is present in the catcher cavity with the input RF field, there are 15 harmonics of the original signal is present. So we can say that signal is amplified by a large amount. Then where are these two cavity klystrons are used, or what are the applications of these two cavity klystrons? That is where it can be used for various scientific applications or experimental application or industrial applications also. It is having the specification like maximum theoretical efficiency is 58%. Typically it is 30 to 40%. Two cavity klystron amplifier is quite noisy. So it is used in a transmitter. So noisy devices generally not used in the receiver. Then it can be used in a troposcatter transmitter, satellite ground stations, VHF TV transmitter, power amplifiers, C-band at an 60 GHz in the C-band transmitters. Average CW output power is 100 to 25, 100 to 250 kilowatt. Then 30 to 60 dB power gain at a 10 to 60 megahertz bandwidth. So these are some specifications and applications for this two cavity klystron. I hope you will understand the things. So next we will have a magnetron and DWT. Thank you.